O'Connor. I'm a Strategic Development Manager for Equans in the United Kingdom. And today I wanted to share some of the learning from the hydrogen research that we've done as part of the Net Zero Northwest Cluster Plan. Now, this was a project to develop a decarbonisation roadmap for the northwest of England, commissioned as part of the UK government programme into looking at how industrial clusters can decarbonise. We've written a pretty comprehensive report, which is fully available to the public. It's published online. And if you've got any other questions after today's speech, please come and visit me at stand F10 at Equans. And also I'll take a few questions at the end. So just before I begin, I just want to quickly introduce Equans because I'm conscious that we are a new brand. So some of you might not have heard us here today, but we are pretty rich in history. So we're the new home for NG's technical services capability, and we've been created to be a new world leader in this sector. With that in mind, we're active in 17 countries. We've got a turnover of about 13 billion euros. And what we're really here to do is empower the three main transitions of our time. So the energy transition, the industrial transition, and the digital transition. And we deliver that by having very integrated engineering capabilities. So as you can see from the kind of ring around the edge, we operate in a whole host of public and private sectors in mission-critical environments. And you can see our complementary expertise are really there to drive our purpose of empowering transitions. And obviously, everyone here today is for the same reason that we think hydrogen is going to be touching on all of those. It's key to the energy transition, and it's equally key to the industrial transition. So when it comes to hydrogen, we have four main offers. The first is about developing integrated hydrogen solutions for industry. So this is from the production of hydrogen right through to the end use, developing up everything in between. So we're a one-stop shop to get hydrogen into industrial sites. And that's part of the analysis that I'm going to talk through in this speech. The second is the opportunity to aggregate consumers into a decarbonisation hub. So here we build up demand in the same area. We multiply different groups together using our kind of broad customer base to be able to bring down costs for everyone involved. And part of the conclusion to the analysis that we've done as part of this cluster plan work is that when you're able to aggregate goods to consumers, benefit from those economies of scale and kind of balance out the peaks and troughs in demand, you're able to reduce the overall cost of hydrogen supply. Our third offering is about blending hydrogen and methane together in a hybrid combustion, and we're really happy to talk through one of our reference projects with a gas turbine where we're demonstrating blends of hydrogen and how it can work on an industrial setting. And finally, we have a whole cohort of mobility settings. So this can be from trains. We refueled the UK's first hydrogen train, but right through to kind of buses, HGVs, refuse. We've got a mobility solution to help you decarbonise your fleet. So given this position in the market, we were really, really pleased to be invited to be involved in the Net Zero Northwest Cluster Plan project and develop this decarbonisation roadmap for the region. So quickly introducing the Northwest Industrial Cluster. So it's made up of those 5 regions that you can see on screen. So we've got Cheshire, Merseyside, Greater Manchester, Lancashire and Cumbria. Those of you who follow the Premier League will know we've got Liverpool, Manchester United, Manchester City. It's a really strong football part of the UK. But it was also actually the home of the UK's first industrial cluster and the birthplace of the Industrial Revolution. So it's a proper industrial stronghold as well. In the UK, 50% of all the industrial emissions are from 6 clusters around the country, and the Northwest is up there amongst them. So it's really important to be able to decarbonise these clusters. Now, the UK has got some really interesting flagship projects to help decarbonise the industrial clusters, and I've just put up a map of HyNet, which some of you may have heard of. Now, HyNet is a dedicated CCUS-enabled hydrogen network, so it's got a CO2 pipeline to store hydrogen in the Irish Sea, and a dedicated hydrogen pipeline that's meeting industrial anchor demands. And the kind of plan around HyNet is to develop this cluster into the kind of one of the UK's strongest hydrogen footings. And as part of the UK's kind of carbon cluster sequencing process, the Northwest has been singled out as one of the 2 industrial clusters that are going to lead the way when it comes to industrial decarbonisation. So there's a big CCUS-enabled hydrogen footprint in the Northwest, but much less is known about the role of electrolytic hydrogen and decentralised industrial hydrogen, and that's part of the analysis that we did in this report. So in 2020, we joined a consortium in the Northwest, and like I said, we were commissioned through the Industrial Decarbonisation Challenge in the UK to develop a carbon roadmap for the cluster to get to net zero by 2040. So we looked at a range of interventions that could be deployed across industry to decarbonize that. So energy efficiency, electrification, a blend of kind of green and blue hydrogen, as it were, and obviously some kind of biomass with CCS. And we were able to demonstrate that by 2040, we can get to a net zero industrial cluster. Now, this is really important because the UK has made some kind of proud statements about wanting to be home to the world's first industrial cluster. So as Equans, we're really pleased to be associated with this initiative. So specifically, when it comes to the electrolytic hydrogen research, we wanted to fill the knowledge gap when it comes to electrolytic hydrogen. There's a lot known about CCUS-enabled hydrogen in the region through that HyNet project, but a lot less is known about electrolytic hydrogen. So electrolytic hydrogen is zero-carbon hydrogen produced for the electrolysis of water. I'm sure you all know that already, but for our definition, it can either be green if it's powered by renewables, or purple or pink if it's powered by nuclear. And we looked at both of these as part of our analysis. And that from here, we were able to basically come up with 4 intermediary objectives to be able to do the analysis as part of our work. So the first thing we wanted to do was design an electrolytic hydrogen production system for the region that was optimized for the lowest overall cost. The second was to explore the scalability of hydrogen for different future energy scenarios. So obviously nobody can predict the future. We don't know exactly where hydrogen is going to be used. So we wanted to model different decarbonization pathways and see the prevalence of hydrogen in each of those. The third was to define different project archetypes and characterize what made them successful. So this would help developers and investors in the Northwest identify the best projects and bring them forward to fruition. And finally, we wanted to examine the practical considerations. And this involved the route to commercialization using the government funding mechanisms that have been announced. For those of you who are aware with UK policy, we've had a number of support mechanisms announced and gone online in the last couple of weeks. And it's really exciting to see how the research that we've done will help bring some of these projects through, get them to FID or financial close. So to do this, we set about on a comprehensive techno-economic modeling exercise to design a system for the region that could produce hydrogen, distribute it, and consume it at all the industrial sites at lowest overall cost. And the first thing we had to do was understand where hydrogen would be used. So we did some modeling to understand the decarbonisation pathways for all of the individual industrial sites, all 161 sites in the region. We looked at their different routes to net zero and how much hydrogen would be needed in their processes. We looked at different future energy scenarios for the gas grid, so how much gas was going to be used in residential and commercial sectors. And we did some kind of tracking of the mobility across the region to see where it could be used in transport. And obviously there's the opportunity to use it in power as well to match up the peak demand. So we match it in the power sector as well. And we were able to see from this map the intensity of hydrogen use in one of our future energy scenarios. So the green area are areas of higher demand, and the red areas are areas of lower demand. Now, you'll notice the kind of coloured in the green area around Liverpool, Manchester, and this is because of the HyNet project. And the strategy off the back of this project will likely lead to the conversion of the gas grid and supplying hydrogen to homes in this area. And actually, Cadent, who are the gas network operator there, have recently announced a home with a village where 2,000 homes are going to be converted to hydrogen. So it's nice to see this coming forth. Now, to complete the modelling, we had to disaggregate the region into 13 jigsaw pieces. And this allowed us to distinguish between, you see, the network-connected area at the south, where we were able to aggregate consumers and kind of model upstream parts of the distribution network, and those decentralised sites in the north that weren't connected to a network, and therefore, if they wanted hydrogen, they'd have to produce it on site or get it trucked in. So we were able to differentiate between both of those. Now, the next thing we wanted to do was understand how hydrogen could be produced. So we looked at the solar development potential across the region. This is the maximum capacity of new solar across the northwest of England. We did the same for onshore wind, offshore wind, tidal, and small modular reactors to understand the maximum capacity in each of the different areas that we looked at across the region. And then the final thing to think about was when hydrogen was going to be consumed and when it was going to be produced. It's quite a, at the moment when you think about gas, it doesn't really matter when you use the gas, so people don't really understand what their gas load profiles are like because there's enough storage in the network to accommodate this. But when you start thinking about intermittent renewable generation, powering electrolysis, and then meeting a kind of supply from industry, you need to understand where the hydrogen, or when the hydrogen is going to be used for each hour under consideration. So we did that for each of the technologies. This is the tidal generation profile for one lunar cycle. We did the same for all the other renewable technologies, and we did the same on the demand side to be able to balance it out. The final considerations were how hydrogen could be transported. So we modeled a centralized scenario. This is similar to the decarbonisation hub that we're talking about, where you can truck by road, but we also modeled one where you had to produce on site if you weren't connected as part of a network. And this allowed us to basically model 8 different scenarios. One with hydrogen consumption, which was higher or lower based on future energy scenarios and how they decarbonize. The modeling configuration, centralized and decentralized, looking at trucking and transport. And a third one looking at the way policy could influence the development across the region. So a target mix scenario where electrolytic hydrogen was incentivized to meet 25% of the overall demand, and a no target mix scenario where it was a pure cost competitive base with CCUS-enabled hydrogen. So we modeled these 8 different scenarios, and from that we were able to understand the scalability of hydrogen in each of the scenarios, but more importantly, isolate the particular variables across the analysis and come to the characteristics of success, i.e. how do we optimize the cost of an electrolytic production system for industry. So the first thing to note is the scalability. There was a very broad range of scalability, and it was actually the target mix that led to the difference. This was a slight caveat on this. We did the analysis in April 2021 before the gas prices went really high. It would have probably been a slightly different picture if we did it now. But the UK has just announced a 50% target for electrolytic hydrogen and 10 gigawatts of production capacity by 2030, which really means we're looking at the right-hand side of this graph. We're talking about gigawatts online before 2030 and 2040 if we're to meet our ambition, and obviously gigawatts of new renewables, which is going to have huge implications across the whole region, but also presents the size of the opportunity in the UK. And although this was interesting, what we really wanted to do, like I said, was isolate the variables, because there's a lot of uncertainty when it comes to kind of energy systems modeling. So we wanted to look at the different scenarios that we ran and pull out the key themes across them and see what made projects successful. And we basically categorized everything in 3 ways. So the first is the electricity source. If you want to drive down costs, it really matters what electricity source you're using to power it. So if you look at nodes 8, 9, and 10, the small green and blue ones, we were able to get down to about £2 a kilogram. And this is because it was operating with a directly connected renewables, avoiding the network costs and therefore the policy costs that are put onto it. If we look at kind of 6 and 12, you can't quite see it on the screen, but they're up over 10, 5 times more expensive. And this is because we had to come up with a more complicated mix of electricity to power the electrolyzer to match the demand at the location. But we also had to rely on grid-connected electricity and bear the cost of decarbonisation that are being put on the grid in the UK. So what this demonstrates is that as we support projects, and if we want to decarbonise the decentralised consumers across the region, there needs to be effective subsidies in place so that it's not a kind of equal playing field between the large-scale, directly connected ones, the dedicated renewables, and those that are able to kind of protect the local jobs and local communities in the areas that don't have a network. But you will notice that from the table in the bottom right-hand side there, that there was no kind of silver bullet, as it were. Like, there was no kind of source of renewables that was perfect. So although onshore wind was the cheapest, we've got a big challenge to getting new onshore wind developments online in the UK. There's a lot of planning. It's really hard to get them through planning, so it was really limited in its capacity. Solar PV doesn't quite have that constraint, but the low profile, only at around 10% for the year, meant you had to really oversize it or have some storage, and it made it quite expensive to operate the electrolyzer. Now, our report goes into detail about how you can stack different electricity sources to benefit from their intermittency to optimize the run rate of the electrolyzer. So although this is quite a kind of crude example on the screen, please come over to F10, as I said, and we can talk more detail about how you optimize the different technologies to power your electrolyzer for lowest overall cost. The second interesting point was about decoupling demand. So if you look at the one on the top right-hand side, this is in an industrial setting where you've got your demand on site, you've got your production of hydrogen, and you've got a bit of storage in the middle. But you need to be able to make sure that you can give security of supply to your industrial consumer, and therefore you need quite a complicated mix of renewables to design your optimized system. In comparison, if you look at a kind of grid blending project, then theoretically, you're able to just operate at the low profile of the renewable technology powering it. So in this case, onshore wind. So we were ramping up and down with the onshore wind, running in the most cost-effective manner, as the actual slack, the decoupling of demand, was built up by the hydrogen network. So again, leads to this point around making sure that these network-connected solutions aren't competing on a cost playing field, because obviously the storage costs have already been sunk between the infrastructure. And then the final point that really jumped out was the require to coordinate across the region. So I put up the thing on HyNet here. Injecting into that to decarbonise that is crucial to the region's decarbonisation. But we also need to have events like these and speak to the energy network operators, to speak to the water utilities, to make sure that we develop places in areas that are cost effective to do so. And alongside that, we also looked at the opportunity to develop decarbonisation solutions alongside other initiatives. So, getting rid of your Scope 2 emissions by putting some additional PV on site. And this helps with some of the curtailment, because that way you're able to use, basically provide another route to market for the solar that you're putting on site by reducing the customer's reliance on the grid in the first place. We were actually able to show that if you considered hydrogen with the other vectors, then you're able to bring down costs by 25%, which is quite a considerable thought. So that's all I kind of wanted to run through today, those 3 themes about decarbonising industrial consumers and optimising it. Thanks a lot for listening. We'll take a few questions now, but if you want any detailed chat, please come to F10 by the entrance and talk through. Thank you.
Thank you for your interesting presentation. I am Nicolas Descourtiers from IFP-IN, a research center in France. My question is, you have shown us how important it is to model the countryside where you are working on. If you are requested to work on another UK region, how easy it is to use your model for another region? What needs to be reconstructed and what is possible to reuse at lower cost?
Yeah, thanks. Really good question. So so basically, this was part of the Industrial Decarbonisation Challenge, and the UK government have developed 6 of these plans across all 6 of the UK clusters. And they're going to be, well, they've actually gone out to tender for a kind of one study to pull that together and share the learnings across that. So I don't think we'd be repeating the modelling as part of this bit of work, but it will definitely feed into the wider UK strategy. In terms of replicability, it's actually kind of almost easier the bigger the scale, because we have to draw the system boundaries in such a way that excludes certain parts of the analysis. So the more you can develop kind of an island that encompasses everything, the more accurate that your model is going to be. And therefore you can able to look at the flexibility between the other clusters as other networks develop. So yeah, we came up with this methodology as part of the analysis. We think it's very applicable for our projects, and yeah, we'd be really pleased to talk about anything like that as well. Thanks. Anybody else? I'll take the silence as I've answered every single question that could have possibly come up and that you all think it's amazing. Great, well...
So maybe you can tell a little bit again about the main factors in the levelized cost of hydrogen. What are the main parts of that?
Yeah, I think... So the way that the kind of network... the way that the electricity costs are structured in the UK at the moment is that a lot of the costs to do with decarbonisation are put on electricity that's supplied through a network. So you've got your policy costs, again, supporting the CFD and things like that, and you've got your network costs for running and operating the network. And if this is kind of stays the same out to 2030 and 2040, kind of as we had to assume in our modelling, then it becomes very expensive to use network supplied electricity. And being able to develop co-located renewables alongside the solution was probably the #1 factor in driving down cost. So looking for sites that are able to have some maybe greenfield land to develop dedicated solar or wind, rather than being purely reliant on the network capacity, was probably the #1 variable, I'd say.
Thanks. Other questions? Last call. Otherwise, thanks very much, Chris.
Thank you. Thanks for listening.